Hi guys, in this video I'm gonna cover a lot of ground, so try to stay with me. For one, I made images available that I use during the videos, and it's available on geronimo370.nl. I'll post a link in the description of the video, and you can see all the images here. Feel free to download them and use them as you please. That's one. Two, I've made a big improvement on SCEPSIS. It's now 64 bits. Sorry, that's a bit much. 64K. We have 16-bit addresses now. And I'm going to show you what that means. It means, among other things, that all the addresses have 4 characters instead of 2. So when I want to give the register A, for example, a value, I can now use 4 positions, as you can tell here. This also means that when I display memory, I do not get a meager 256 bytes, but I can go on and on and on and on, see the numbers going up. I can go all the way to, this is FFFF, which is high values in 16 bits. So we have 64 kilobytes of memory available to play with. That's a lot. We're almost never going to use that at this point in time. That's the memory, 16-bit instead of 8 bits. Next thing. In the meantime, I've been working on an assembler. We can go to issue number 29 on GitHub. I wanted to be able to use the assembler as a command line instruction like this. When I specify a source file, then it is going to react like a command line command, and I could also specify an object file where the executable code is stored, and even a file where the listing is produced. But also, when I just say, let's type it correctly, it will still be an interactive program in which you can, by using the source, object and list commands, use your own files. But I thought it was convenient to have a command line option as well. This is the way you assemble. Now an object has been created in the file sepsis.memory, which means that's the default file. When I type load here, I go to the memory. This is the assembled code that can be executed, and this is the prime program. The prime program calculates prime numbers from 1 to 4095, 8 bits. When we run this, I'm gonna have to abort it in a bit. That's a bit unpleasant, but you see that it spits out prime numbers here. So now I'm going to abort it. Just check it out at your own convenience. So that was the command line option. Next thing is that I have built-in assembler directives. I hear you ask, what in heaven's name is an assembler directive? Well, we have seen assembler instructions, like load A immediate, for example. That's an assembler instruction, and that is being assembled into memory as an opcode and an operand. Assembler directives do nothing of the sort. An assembler directive tells the assembler program that it has to do something. For example, I have made 4 of them. Base, I'll explain each of them in a bit by example in another tab. With base you can specify an address in one of these formats. DC, declare constant. You can declare data that goes into memory. You can also, you can also define storage, where you only have to specify characters for a length of and then a number. That storage will not be initialized. And then you can have the equate assembler directive, which just states we are here. I'll let you have a look at some code that I used to make the assembler directives clear. There is a listing of the dir.assembler program. When I compile this, no, that's a bit too much of a hassle. I've compiled it. This is the listing that comes out. You can see the equate here. This asterisk doesn't mean anything, but you can see that it takes the current address 0000 for the main label. Does the same here. I'll explain why this is a gap in a bit, but it's at address 000F because we are here at address C. This is a 3-byte instruction, so C, D, E, and then the next address will be F. So equate takes care of assigning this address to this label. Right here. Now, well, we do some stuff, and then we say jump to loop. In the second pass of the assembler, the labels that are used in the instructions are translated into addresses. So the label loop is being looked up, that's here, and it has address 1000, hexadecimal of course. And you can see that the jump instruction has an operand of 1000. That's being replaced in the second phase of the assembly process. Now we come to the good stuff. We have seen the equate, but here's the loop, and at the position of loop I stated that the base is x1000, hexadecimal again. So that means that this loop will not be coded at address 0f, but at address 1000, because that's what we specified. So we can scatter our program through memory. Sometimes it can be handy. So that's how base works. Now let's go a bit down. Here we have another directive, and that's called define constant. And you can see that there's a constant here. That's a lot of hexadecimal characters, and when you compile this you will see it show up in memory. This has a length of, if I remember correctly, 15 or something. So the address skips 15 after the definition of this constant, and this just goes on to the next address. That's why I had to skip over it here. The program basically does nothing, but it serves as an example. This is the ending of the program. It specifies the halt instruction. And here you see an uninitialized piece of storage of 64 bytes in length. And after that you will see a define constant ABC, which is hexadecimal 414243. This length I have to adapt the listing. This doesn't show up very properly, but I can also specify binary constants. This piece of garbage amounts to 2 AAA, and 4095, which is the highest possible address. No, it's not. The last address under 4K is 0FFF. That's a decimal specification. Those are the assembler directives I built in. Well, I would like to show you this one. So let's go to the assembler and say source file ./dir. That will take care of that, and then I want to change the listing file. Yes, and now I can assemble it. It has been assembled to sepsis.memory, which is the default file again. So when I, just checking, yes, when I type load here, and we have a look at memory, we can see that the first part of the program up until, let me check, oh, here's the 40, and this is the jump instruction that we find here. So now we have to go to address 1000, and here's the rest. I'll go back a bit. No. Here we are. This is all zeros, uninitialized memories. And here we have the E8, which we have here. And so the rest of the instructions, and here we have the, we should have this thing, 1, 2, 2, 3, etc. Oh, here we are, 1, 2, 1, 2, 2, 3, 3, 4, etc., 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 all the way up to FF here. And after that, we have the 20 instruction, 20003. You can see that here. Now you can see that this is an assembler directive because it doesn't take up any storage. It only tells the assembler what to do. And then we have our hold instruction, which is here. And after the hold instruction, we have defined storage, uninitialized, for 64 bytes. And that is this piece. That's exactly 64 bytes. And behind that we have the 414243, that's ABC. And then the 2AAA, that's this one. And then one last 0FFF. This stuff. Well, that says a bit about assembler directives. Now I want to take you back, if you don't mind, to our prime program. Which I think is still the default. Yes, here we are. I'm going to compile this one. Oh, that went a bit quick, didn't it? Yes, it assembles correctly into the default storage. So that means that if I go here, let's stop the program to be sure. And we do a load, and then we have a look at memory. Now we look at our prime program. Why would I want to show you this? Because I improved the animate function. If you have had a look at the sepsis.config file, you could have seen that there's an animate keyword in it, and I've improved the functionality of that, so that when we specify, namely this one, then it only refreshes the screen after execution of the whole program, when it reaches the hold instruction, or, and this is what I added, when the out I control signal is used, meaning that there's something, a value, being put into the output register. That's what I want to see. So we go back and now I'll have it run. This is a program that calculates prime numbers and it puts them in the output register. I'll show you what happens. It only refreshes the screen when a new value is found. This speeds up the process. Where earlier I did not have the patience to wait even till 3.0, I can now, in a reasonable time, see it go over FF, so to 101. That's the first prime number after FF. So this has made a considerable improvement in the processing speed, because it didn't have to show the screen every time. I'll stop it now. It's a bit clumsy, but that's how it works. So that was the improvement in the animation. One last thing I want to show you, and therefore I have to close a lot of stuff. Let's go to the language definition file. That's here. What I did, hold your head, I made a call and a return instruction. And I can show you that in a program. Go to source, call and return. Let's have a look at the program. Here we are. It's almost nothing, but it works. Check it out. It's on the GitHub site. It's a very simple program. I'll have a look at the listing, that's more readable. It starts with a main, then it specifies a call to subroutine 1, and then a halt. This call to subroutine 1 is handled completely without using registers. In the microcode below it, I dare you to check it out and see if you can understand what happens. It increments, or it changes, I should say, the program counter to the address of this label, which is here, which has a base of 100. This is a subroutine where it does something, and at the end of the subroutine it specifies a return instruction, where this call pushed its return value on the stack. The return pops the return value from the stack and then jumps to it very plainly. So this is a very neat solution to be able to have subroutines in assembler. Well, that concludes the video for today. Thank you for watching. I hope you like these videos. Give me a like or a thumbs up or whatever, and check it out. Thanks, guys.